Okay, so hi everyone. Today we're going to talk about deep learning, and I know probably a lot of you are maybe excited to get into neural nets, but today we're
Didn't
actually
do the little recordy sound.
it didn't. Ah, well then, I pressed record, so well. Okay, well, we're gonna cover because deep learning is a pretty complex topic. We're gonna take it pretty slow, and today we're gonna look at reinforcement learning, and probably next time we're gonna start getting into neural nets. Okay, so let's get started. Okay, so what is deep learning really? If you think about it, there's AI, which is a big like subfield of CS, and then within AI you have machine learning, right? And within machine learning you have deep learning. So it's a class of machine learning algorithms. And the reason we call it deep learning is because you have multiple layers. And what I mean by layers is that when you have like neural networks, you'd have multiple layers like stacked on top of each other. It's trying to mimic like the human brain, like with the neurons and like that network path. So like with your classic machine learning algorithm, it's normally just like, one algorithm. It's like one layer kind of, or one function that you pass information through and then you get an output. But with deep learning, you're going to pass it through multiple layers, multiple nodes. Yeah. So deep learning has neural networks and reinforcement learning, but actually, so reinforcement learning is kind of in between ML and deep learning. Like reinforcement learning commonly uses neural networks in it, but technically the way of learning itself, I think, is a machine learning technique. So there's a little bit of a difference in that. But what makes deep learning special is that it automatically does the feature extraction for you. So if you remember from our past GAs with like ML and stuff, you have to have your data, right? And normally you either have supervised or unsupervised machine learning, and that depends on what kind of data you have, which is sorry, labeled or unlabeled. And really, even with the unlabeled data, sometimes you normally have to do like that feature extraction by yourself. So you're thinking like you want to classify, okay, like you have a bunch of houses and you're trying to predict like the price or something. So you label like how many rooms it has, square footage, and those are your features, right? But deep learning will kind of figure it out by itself. It's also known as feature learning. So if you just dump a bunch of data on it, just like dump a whole bunch of stuff on it, it'll figure it out by itself. And it does really well with large quantities of unlabeled data, which is great because obviously nobody wants to hand label data, especially large quantities of it. And if you want the more data, the more accurate your model is. So with deep learning, deals really well with large quantities of unlabeled data. So really, there's not much like data processing you have to do for it. You can just kind of, dump it in there. It'll do fine. So here's some examples of applications of deep learning, but we'll probably talk about the applications. I think we have a later slide for that too. But if you think about like image processing or object recognition, there's several different like questions kind of it has to ask itself, like, oh, what is this object? Is it, blue? What size is it? What shape is it? All there's a lot of different things you have to figure out before you can determine what object it is. So why deep learning? If you look at the graph over here, deep learning is okay. Well, first of all, deep learning is more newer-ish and it's still developing, but with the amount of data, a lot of learning, like older learning algorithms, they don't really improve after a certain amount of data. You just kind of like it just kind of levels out, but deep learning will continuously keep improving with the more data you like shove onto it. Okay, so how is it different from machine learning? So as I said earlier, deep learning is a subfield of machine learning. So really, oh, this is a good image of it. So you always have your input data because whatever you're training on, you have to have data. And you normally have to, hand pick out what you want it to like look at. So maybe you want to look at square footage and compare that to like housing prices. Then you're gonna have to go through and label this is square footage and like for this house or have label your data, for supervised machine learning. So you have to deal with the feature extraction by itself, and then you feed it through your algorithm, and then it gives your output, right? But for deep learning, it does the feature extraction and the classification all at once. So you kind of just, like I said earlier, just dump data on it and it'll figure it out. So yeah, ML uses mathematical algorithms, but then again, so does deep learning kind of, but not too like ML is more straightforward about it, if that makes sense. Deep learning layers algorithms. So it's not just like one, like linear function, this amount of square footage gets you this amount of like price for the house. No, you have to, there are many different layers that you feed it through. So you have a bunch of data, you feed it through layers and layers and layers of algorithms, and it's trying to mimic, again, human intelligence. So yeah, it's modeling the brain. Okay, and here's just a diagram that shows artificial intelligence, machine learning, and deep learning. So I think I said earlier too, but artificial intelligence is like, your broad subfield of CS, and then you have machine learning within AI, then you have deep learning within machine learning. So think of deep learning as like super advanced layered machine learning. The keyword here is layered because the word deep, remember, comes from the layers. Okay, so we're going to get into reinforcement learning today, which is, I guess it's like, it's not, it uses deep learning concepts, but it's technically an ML technique. So there's some keywords that are like specific to reinforcement learning. So let's go through that real fast. But first, before I get into this, reinforcement learning is, kind of what it sounds like. So imagine training a child. So you want your child to do certain things and you don't want your child to do other things, right? So you reinforce their good behavior and then you like sometimes reward or sometimes punish, and that's how you train your child. And I'm saying train your child, and I know that's kind of awkward, but well, okay. So your agent is whatever you're trying to like train or whatever you're putting in an environment. It's the entity that's going to perform your action. So that's going to be your agent. And your environment obviously is, your environment where the agent is, it's the setting, but the state is not exactly like the environment. So the state is the current situation you have returned by the environment. So like if I'm in America, right? I'm in Texas, we all are, but the state of Texas, state, not like as in the state of Texas, as in like 50 states, as in like the situation Texas is in. So like, actually that's kind of a difficult topic because I don't really know what state Texas is in. I guess it's cold right now, windy, kind of like that. So the current situation. So you have your setting and then you have like what's happening with the setting, kind of your environment and your state. And also, depending on what kind of reinforcement model you're doing, sometimes state can imply state of the agent. So you have to be careful. You need to clearly define what your state is going to be when you're making reinforcement learning models. Otherwise, it's, going to screw up really bad. Anyways, so you have your reward, and it's also pretty straightforward. It's basically an immediate return after the agent does something. So if your kid gets an A on a test, cool. Give them like candy or something, I don't know, a reward for a child. And then your policy is how the agent decides what to do based on the current situation. So basically it's what is the agent going to do right now. So if your overall goal is to, get somewhere, I guess, like get from point A to point B, and you need to like make some turns, or instead of going straight from point A to point B, say there's like an obstacle in it, your policy at that point, if you're in front of your obstacle, is not to go straight because the current situation is there's an obstacle right in front of you, so you need to either turn right or left to go around. So the policy is what you need to do right now, kind of. Your value is your overall reward. So what you're trying to do with reinforcement learning is you're trying to maximize the value. So I'm gonna go back to the training a child example with like tests and like good behavior. So you need to try to maximize however many like treats or rewards you get, right? So you're gonna try to maximize, the good behavior while minimizing your bad behavior, of course, right? And we do this with the value function, V of S, and S is the state. So We'll get into like the actual function and stuff in a second, though.
Okay. So reinforcement learning basics. So basically, this is like a method that's concerned with how agents act in their environment, just as Tiffany just said. It's a basic paradigm. We talked about this earlier. If y'all remember, that was our GA like 2 weeks ago, I think. 2 weeks
Yeah, I
ago.
think so.
We did unsupervised and supervised learning. This one is different from those in that it needs no labels or data sets, which is kind of more like unsupervised, I guess. But this one is a lot more efficient with larger data sets, which is something that both of those clearly lack. Simply because it adapts to an environment. That's the goal of this. It optimizes decisions to maximize its total reward over time. That is the best way you can characterize this kind of function. So reinforcement learning, I mean, like, just in that line, you can kind of think about it. You're optimizing your decisions to be best that you get the most goodies from the perspective of the agent, which is like a kid, I guess. If we're going to keep going. So yeah, don't need any labels, no input output. You have like a balance of exploration of new rewards, which is basically like so basically you're gonna have like I'm gonna get into this later, but you're gonna have like a learning rate, and basically this is like this is a reflection of whether it's optimal for your data set to go and find higher rewards. Like it changes the way it weights data, right? So I mean, I don't know. I'll be more specific in later slides, but basically, you want to find a balance with your reinforcement learning between finding new rewards, going out and like looking, in the upper cabinet for candy, or trying to get the one that you already know of that's in your parents' room. I don't know. Getting too far, but I mean, like, I think you understand. The cool thing about it is, I mean, like, this is things that are pretty. I feel like reinforcement learning is just generally intuitive to people. This is how you learn. So the difficulty is applying that to a computer, because although we think of those things and it's like secondhand, it's not the same for a machine. But the cool thing is that even though machine learning, sounds like some like foreign, like weird, like cool sci-fi concept, it's really not. And like when you break it down, I mean, like, especially with like something like reinforcement, it's like, oh wow, it literally is a machine, learning how to do things based off of data. And then the cool thing about it is it can reflect onto us, and we can kind of like see like insights into like, or like, I guess you think more critically about how you are thinking, because we're applying ourselves to those computers to figure out how to make these algorithms. Anyways, aside from my tangent, because you're having a balance between exploring and then exploiting rewards, you're going to have a balance between long-term reward and short-term reward. Okay, so what that means, I mean, usually this is something you define for your model in the function that basically handles what is it? I forgot the term. I forgot the word. Could you go back to the last slide? What was it?
Yeah.
Other one. One more. One more. Okay. But no. Forward. No, forward one. Okay. Forward another. Like forward two. To the feature extraction.
Feature extraction.
Okay. So like the
Oops.
feature extraction and classification part. Basically. Crap. Okay. Anyways, like with feature extraction and classification, that kind of ties into how your model is going to be saying short term versus long term. That's how it's going to be classifying data. I mean, like this is that part of the stage. Okay, so basically, how your model sees things and determines whether or not it's worth it to just stay where it's at or update the model towards something new is that middle part that we saw right there. A challenge of all of this is that you need to have parameters for this and you need to define them. So you're gonna have, I mean, like the largest challenge really with reinforcement learning is knowing what parameters you need to set. Does your model need to adopt new things and new reward? Like, does it need to look for new rewards more readily? And should it be adopting like new policies and values more readily, or should it stay with what it has and not change very much? These are things that you kind of need to develop into your system. It's very involved, as it says on the slide. Also, another thing is like when your environment isn't stationary. So like, I don't know why, but I kind of thought about this whenever I was making the slide. Um, I'm not sure if this is a good example. This is probably gonna flop, but I kind of thought like you have like Americans. All right, let's go back to the American Revolution. Okay, um, don't know why, but Americans lived in America for about a century or so at least, or most families and people were here for like at least like a good century or so beforehand. Like the Mayflower was like in the 1600s or something. I don't know. But anyways, uh, point is that like they knew their environment. They'd been there for a long time. So even though they came to America, they didn't know anything. Um, they'd been learning in a stationary environment. You can kind of think about it like that. So when they fought the British, who had never been to America, who were coming from overseas and traveled all this distance and are used to British weather and British climate, and not, guerrilla warfare tactics, they march onto the field and all this other stuff. They got destroyed, even though they work like reinforcement learning, just like everybody else. They didn't have a fun time fighting in America. Um, this can be a very very big issue whenever you are building your. I'd say if I had to rank like the challenges of reinforcement, it's defining your parameters is the largest one. That's the hardest thing to do. To know like what makes. I mean, because parameters basically determine like the speed of how fast your model will learn and get its job done. So that's number one priority, biggest challenge, and then the second would probably be like your environmental conditions. If that's something that's changing often, then your model will have to adjust a lot. Another thing that can happen is if your environment isn't changing too much, you get a state overload, which basically the way you can kind of think about this pretty simply is it's like how we talked about overfitting versus underfitting. So this is like overfit, probably a bad comparison, but I think it gets the idea across to think about like state overload is like overfitting a data set. So basically you have too many states that your reinforcement, like your model that's using reinforcement learning is considering, and it's getting too specific with its predictions. And I don't know. I guess you could maybe you could call this like giving the kid too much candy. I don't know.
Actually, that's a good example because, like, if you think about it, if you live like one place your entire life, or maybe say you're confined to your room for your entire life, as soon as you step outside, you're gonna be disoriented because you don't know. You've learned very clearly what like where everything in your room is, but like not so much around the house. So if you try to do the same things that apply to your room to the house, you're not gonna have a good time. So that's when it gets like too specific, if you know what I mean. Your model gets too attached to that one environment it is, and it can't do it any better in the other ones. So like you reinforced it too much, kind of. So now all you know how to do is like whatever you're giving your kid candy for. If that makes sense. Sorry, that's kind of a
No, that one works.
Okay. Okay, so here's a good map of reinforcement learning. You have your agent, which is, whatever is doing your action, and then your environment. So if it does an action that you like in the environment, you take action to your environment, then you're like, okay, cool, I like this. So you give it a reward, and give it, and then your state updates. Your state becomes something like, because if you do an action, your state isn't going to be the same. But also, you before you give your reward, you also have to observe the state. So you think, if you like, okay, I'm going to go back to the child example because that's a really good example. But if you um drew all over the walls, actually no, I'm saving that for a different example. We'll use that for negative reinforcement. But if you like got all A's, or your GPA is really good, whatever, you took action, you studied, you worked hard, you got your A, and then you got your reward from your parents, most likely, and now your state is 4.0. So you observe your state and you're like, cool. But let's say you got a B, and then your GPA went down. So that's your action. Like, you got a B, that was your action, and you probably wouldn't get a reward for that. Maybe not, Asian parents, I don't know. But you observe your state and your state drops to, like, I don't know, 3.8 or something. So you just keep doing that over and over again. So then your agent will learn that getting A's will raise your GPA, which is what you want, and you get rewarded for that because it's what you want. And then you just have to continuously keep observing your state until you accomplish what you want. So I guess this will never end until you get out of college. But yeah, you have your like neural network here. So you're at your state, right? And you're trying to determine what you need to do. And like Joaquin was saying, your parameters is like what what kind of restrictions you have, kind of. So you obviously uh back to the school example, I guess a parameter could be like no dropping out or something like that. Or that's you can't just call it quits and go to community college. I don't know, drop out of college, just get a job, McDonald's, good. But yeah, so oh yeah, your policy. So sorry, I almost forgot to mention this. Your policy, normally they mark it as pi for some reason. I don't know why, but policy. If you see pi in like reinforcement learning, it means policy. So your policy is, remember, like what you want to do based on your current state. So we have your current state S and then the action A. So your policy function is kind of thinking like, if your state is at a 4.0, you actually, to be honest, you don't really need to like, okay, I was gonna say you don't need to take action because you already have a 4.0, but no, you still need to take action until you reach your conclusion, which is, graduating. So your best course of action in that point would be to, get an A. To be honest, your best course of action in this situation is always to get an A. So your action was always going to, get an A, but that doesn't always happen. So yeah. Yeah, that example is kind of limited because the options are really, like the best option is always to get an A, but sometimes if you're like, sometimes, okay, in like a different situation, sometimes what is immediately the best course of action may not be the best course of action in the future, if that makes sense. So, okay, yeah. Oh, here we go. So you have types of reinforcement learning, which is positive and negative. And like Joaquin said earlier, this is, fairly intuitive. You get a reward if you do something good, or, you get punished if you do something bad. So normally they do positive reinforcement and sometimes they do negative reinforcement, but I personally think it might be best to do positive and negative reinforcement. So obviously positive reinforcement learning, if an agent did something good, reached a good event, then you get a reward, and increases the strength and the frequency of whatever action the agent did, the event, and it maximizes your performance, right? So it also sustains change for longer. But like Joaquin was saying earlier with state overload, too much leads to over optimization of the state. So, oh yeah, golden child syndrome. that is if you've heard of golden child syndrome, it's when like you were really gifted as a child and everybody was like, wow, good job, you know, you're so smart, you're a genius, and then you grow up and you realize, wait, I'm not that good. So golden child syndrome is like if you're constantly praised as a child, constantly rewarded, then later that kind of becomes like your baseline. So if you don't always get rewarded, you just kind of throw a fit. You don't know how to handle it if you're not, you know, getting perfect A's, top of your class, like first chair or whatever. So that's why you have to reward sparingly. Although that example is kind of based too much on humans because obviously your AI entity or your machine isn't going to develop, you know, golden AI syndrome or something, but it will start to over optimize. So, like, if you give it a really good reward every time. Oh, there's another good example of this, like with lab rats. I think they trained them to, you know, press a button to get food or something. So really all they did was just press that button over and over and over and over and over again until they like got super overweight. So obviously that's not good, but that's over optimizing the situation. So with negative reinforcement, I think is also pretty intuitive. Don't, if you do something bad, of course you're probably gonna get punished. So this is where it'll deter specific events, but only specific events. Like whatever you punish the machine or your child for, that's what it's gonna deter. So let's say you drew all over the walls as a kid, which I did with nail polish. Not a good idea. I got yelled at. But after that, I knew not to, you know, draw on the walls with nail polish. So, but it didn't encourage me to do anything better. Like whatever, I don't know what better is in this situation, but all it did was don't do this. So that's your minimum standard, I guess, is to not do a specific event. And of course, it doesn't maximize your performance. If you only punish your child if they get F's, they're probably not going to strive to get A's. They're just going to be, if you get a D and your parents are okay with that, which they probably aren't, but if you get like C's and B's and your parents are cool with that, cool. Like, if you only get punished for getting an F, then you're only going to avoid getting an F, and you're probably not going to always try to get like 97 and above, you know? So you have that minimum standard, and that's really all you're trying to avoid. You don't really go out of your way to maximize your value, if that makes sense. So, but yeah, it's better at encouraging behavior. And what I mean by that, like a reward will of course encourage behavior, but a punishment will be better at reinforcing it. So like, you know, I'm sure you guys can remember whenever your parents punished you for something, you never wanted to do that again, right? But if you got a reward for something small, you thought, cool, this is a nice reward. And then you didn't try to like do that action over and over and over again for like a small reward, right? It was just like a nice thing that happened at the time, but it didn't necessarily really push you to do that again. But with negative reinforcement, of course, you're going to make sure you never do whatever angered your parents so badly ever again. Okay. Yeah, so that's positive and negative reinforcement learning, which again is fairly intuitive, right? You know, reward for good things, punishment for bad things, and you try to steer your AI on the right path. So this bonus brute force is not really a type of RL. It's more of a algorithm. So it actually belongs in the next slide, but I had space here, so I put it here. Basically, this is where if you have your AI in like a room with like interconnected rooms and you're trying to get it to go to like the end room, but you need to like a maze kind of, you need to like turn this way or turn that way. So brute force will basically go through and do every single possible action. So like if there's like a right and a left path, then go to the right one and then like go to the right and right again, and then you go to like right all the way down to the second to last one, then you go left, and then you go right to the third to last one, and then you go left, and you know, it branches off. You do every possible single action until you find whatever you want. But that obviously doesn't work really well. It works, but only in very certain situations where there's not a lot of pathways. Most of the time, that's not the case, so I advise not to do brute force on most of this stuff. Okay, so reinforcement learning algorithms. We have two main ones. There are a couple of more, but those get super in depth. So maybe Henry will talk about them in his later advanced AIs, GIs, but we'll see. I think that they're still on they're doing naive Bayes right now, but that's also a whole different can of worms. So we have value-based and policy-based reinforcement learning algorithms. What the value-based ones are, again, I think I mentioned this in the glossary, like the terms. So you're trying to maximize your value function v, and then value depends on the state, right? So this, however, looks at the long-term return of your policy. So it might be good to, get the small reward over and over again, but what if you could get a big reward with like, more steps? So instead of doing one action over and over again, maybe take two actions and get a bigger reward, stuff like that. So this is trying to get the greatest yield of reward. So with that, as I was talking about earlier, you have your current policy and your optimal policy. So your current policy is what needs to be done at that moment, at that state. But it's probably like if you had like $5 in one room to the left and like $10 two rooms down, your current policy, what should be done in that situation was probably go to the next room and then after that to the room with the $10, right? Because you want that max yield. But the best, so yeah, that doesn't necessarily have the best return yet. Your current policy, you're trying to get, it's what you want to do now, currently, but just remember that it's not always, the quickest solution. Okay, and your optimal policy is the one that gets the best return. And if I remember correctly, it's the one that gets the best return immediately. So this one would be going into that room with the $5 and getting that $5 and being satisfied with your life. But it's probably not a good idea. Then you have policy-based reinforcement learning algorithms. So there's is also called direct policy search. So I've seen this called policy-based or direct policy search. Anyways, there are two different like types of policy-based. So there's deterministic, which maximizes reward, but it's also really easy to counter. So an example of this is rock, paper, scissors. So if scissors has the best overall probability of winning, so like maybe scissors wins like 40% of the time and like rock and paper win 30% of the time, then the deterministic algorithm will just choose scissors over and over and over again because it has the best probability of winning. But obviously, if you do that over and over and over again with somebody, you're gonna lose after like the third or maybe fourth time. So stuff like this, the deterministic one just goes with the best chances, although that's not always the best one, especially if you're like playing against somebody or like with a different AI. So yeah, they do maximize your reward, but they are really easy to counter. So that's the problem. As soon as somebody figures out, oh, all you're gonna do is play scissors, obviously they're gonna start playing rock. Then you have your stochastic policy based. So that word really just means random. Like if you search it up, it's just a really long definition of saying random. So every action, of course, has a certain probability and it introduces randomness to your algorithm. So for example, rock, paper, scissors, it's probably a much better option to randomly pick one and play, and you're definitely going to get a better result than, or like you're going to win more times than if you just did scissors over and over again with a deterministic algorithm, right? But another situation where stochastic comes in handy is, let's say you're having your AI like you buried something and you just have to dig through like random plots to find it. So with the stochastic policy based, you're gonna just start picking random like plots. You're gonna go like, oh, maybe this corner or that corner in the middle, something like that. But it'll probably be faster to do it randomly like that than to do every single one in a row, if that makes sense. So like, because like, what if it's at the very end? It's gonna take forever. But if you do stochastic, then it's kind of like sampling. Like it's a good way to see like things throughout the field rather than just, slowly combing through everyone, right? Although the deterministic one will definitely, actually, both of them will definitely find it because once you run out of options, it's got to be the last one, something like that. But with the stochastic algorithm, it's slightly more likely to find it faster. And especially with really really big data sets, stochastic it's going to be much better or much more much faster, right? Because if you think about it, if you're going through every single data point trying to look for something, then it's going to take a really long time. But if you just kind of randomly poke around, eventually, well, it'll also take a while, true, but it'll take less time than trying to go through every one of them individually like that. Okay.
Alrighty, fun math time. Okay, so our first type of reinforcement learning is Markov decision process. This is the simplest one and it behaves like a Markov chain. Um, those basically, I mean, like, I've made it way too small, but you can see a super simple one at the bottom. It's basically like a probability tree. So we've done this stuff before. It's kind of similar to I think it's supervised learning. Yeah, in supervised learning, we talked about like how you can model weather with a Markov chain and like basically like base your decisions for like a day. So like if rain, then 50% chance of cloudy. If rain stops, then if rain, then 10% chance of sunny. So on and so forth. But you can do like a similar thing with reinforcement models, and this is what I was talking about before, which is the feature, like the feature part and the classification part, with this equation right here that you see. So you have the value is the sum of your probabilities that you obtain from your certain policy at a set of states. So basically, for for the model that you're building, the reinforcement learning model that you're building, I'm just going to use these terms and try to go through it kind of like quickly, because I mean, like, I don't know. I feel like this isn't too deep. We've kind of covered this stuff before, and you can understand it kind of like, I mean, like you can already see right here with our reward process, it's sub our policy, which is basically saying it's based off of our policy for a set of actions. This right here, I hope you recognize it, the R term. This is basically like the reward function. I mean, not reward function, the optimization function that we had for linear regression. This is kind of like a similar system, except this time we're basing it off of it's kind of like a different parameter. You have sets of states, and you're optimizing those sets of states, and you're looking for a maximum of your value, your value. I mean, your value, which is defined by your set of states, as you can see on the left-hand side of this equation. You have gamma, which is next to you can see gamma multiplied by the value with S prime, which is you maximizing your values or minimizing. I'm pretty sure that could vary based on whether you're doing like positive or negative reinforcement learning. So to do like something like negative, you're basically figuring out what's wrong, and you're moving towards that. You're figuring out what you shouldn't be doing, which is one thing that you can do. And then maximizing is the opposite. You're figuring out what you should be doing. Yeah, I mean, this is a pretty succinct thing. Basically, what you're doing right here is like you're adding up all of your rewards, and value is a cumulative function. It's a sum of all of it's a sum of the rewards that you get for the actions you've done with a set policy by your agent. And you can see down here, R is defined by gamma to the T. Gamma, I'm pretty sure that stands for your, I don't know. I thought about it as decay. What was it again? It's your discount. I think it's called a discount rate, which is basically like looking into the future. Your discount rate is like how good will it do you to look towards a future reward. So I guess the discount part is like saving up. It's kind of like would it be better for you to save up and look towards like a further reward? Kind of. I mean, I feel like that's a bad way to word it. But I mean, like the essential part to it is it's optimizing for a later reward. Um, yeah, and then you can see it's defined by little rt, which is like the current reward at that instance. But yeah, I don't know. This one it's relatively simple. I mean, you definitely don't need to memorize this kind of like equation, but it's good to understand it because I mean, like if you were going to build something like this, uh, you'd have to program something that works like this function. I mean, like this function right here does the same thing that this Markov state diagram does. And especially, I mean, like basically, like how Tiffany said earlier, you're going to be building these on top of each other. So you have multiple, you'd have like, multiple of these probabilities for your rewards being built up coming to your total value. Yeah, I don't know. I'm bad at making all of this very what's the word? Simple. There you go. Simple. I'm bad at making this simple. If y'all have any like questions, or if I'm not being clear enough, you could throw that in the chat. But otherwise, we can move on. Okay, so quality learning, Q learning, basically, it works on a similar system, but this time you have a value array of all of those values. This is more like what I was saying. Basically, you're having multiple values, and they're associated with actions, and it informs the agent of which actions are the best and which get the best. Like I mean, like as you can see in this table, so you have you're defining your Q table by states and actions, and basically you're plugging stuff in, and you can see return values for which your return values are telling you which Q is the best. I mean, I guess I could put it like that. And I'm pretty sure Q doesn't stand for quality of action in the function. It stands for, or does it? I'm pretty sure Q just works like the same kind of value. Yeah, Q just works like the same kind of value. But what you can see down here at the bottom, that's called, it's a type of Bellman function. Basically, those are functions just like the last one you saw that work on the Markov decision process. And it's basically just iterating values. So as I said before, you can see the discount factor, which is gamma. And it's being multiplied by the max of the optimal future value. So this is the value that's going to come after what you're calculating. Or yeah, I mean, like a way you can think about this, if y'all have done like a recursion or not recursion, you're iterating. I mean, there's no that's the simplest way to put it. You're iterating values, and it's kind of like recursion, I guess. You have your old value. You have your optimal estimate, and your discount factor is basically saying, okay, should I how much should I value this future value that I have? Is it super valuable? Then you're going to have it as 1. And this is something that ranges from 0 to 1. I should have clarified that. But your discount factor basically tells you how valuable that future max of Q is, that value. And then your reward, you add on your reward from that value. Okay. So that's like a specific instance for the t you're measuring. Okay, and then you have your old value on the left hand side, as you can see, and then your learning rate. You can think about that kind of like I guess a pretty easy way to think about it is like nuclear decay. Um, so basically, what I mean by that is like it's telling you how much your old values mean. So discount factor tells you how much you should go towards new stuff, new rewards. Learning rate tells you how much you should stick onto the stuff that you already have. You know, it's called learning rate basically because it's just like how fast are you going to be learning new things. You know, and it basically inhibits. Like let's say if your learning rate is 0, then you're not going to really be taking on any of your. I mean, like you can see it right here. It's multiplied by that new value. If you have a learning rate of 0, you're not learning anything. So you're just going to be sticking with the same model. If you have a learning rate of 1, then you're taking on every new reward value that you have, and basically adjusting this Q table that you have. So you're going to have different information on the values of your arrays and what works best and what doesn't. Something that I should point out with this is that your Q table does not have a policy. I hope you notice that in this situation. There is no pi value for this, so you don't have a policy for this. It's going wild. But yeah, as you can see right here, explore, exploit, randomly taking action, may discover new states. So this is, it's just doing its own thing. There's no like set direction for it. Policies are kind of like how Tiffany was talking about with the rock, paper, scissors. So like let's say your policy is like scissors works best. You don't have that kind of thing for this. It's figuring out everything on its own. So like let's go back. Like you could look at the Markov decision process. That one uses policies, and that's something that you can add to it that might help the model learn. But this one just doesn't have any of that. I guess this is kind of like in pseudo terms, unsupervised reinforcement learning. Although that's probably a bad analogy. But anyways, we can move on.
Yeah, I think that kind of works for the analogy, but yeah, let's move on. Okay.
I was unsure about this.
Okay, I can do it. So this is just a little bit of sample code for the epsilon learning. So with Q learning with epsilon, sorry. So, yeah, there's a point here that says balance exploration and exploitation with epsilon. So you have your epsilon value E, and we're just gonna set it to however percent you want to explore. So let's say you want to explore 20% of the time and exploit 80% of the time. So you're gonna set E to 0.2. And then the way this code does it is it just finds a random number between 0 and 1. And then if it's less than epsilon, then it'll choose to explore. So it'll just, do a random action, or yeah, it won't follow the Q table and it'll just do something random. If it's greater than 20, or not 20, 0.2, then it'll choose to exploit. So it looks at the Q table and it's like, okay, which path will lead me to the best reward? And it'll follow that, if that makes sense. So basically it's just, I want to explore 20% of the time, or maybe 30% of the time. You just set your epsilon value to that percentage and then pick a random number. Probably they're doing it with like 0.2, but personally I would probably do it with like 20 or something. Actually, no, because epsilon is typically like a really small value, but you could just set a random variable. Like I would set, if I wanted to explore 30% of the time, then I'd just set something to 30, and then I'd have a random uniform number between like 0 and 100, because that's just what I would do, but this works too. And I guess it works out kind of better this way because epsilon is typically like a really small value. But yeah, either way, basically you're just, randomly exploring however many percent of the time, and then the rest of the time you're exploiting based on your Q table. So yeah, that's pretty much it. It's pretty straightforward.
Okay. So we talked about all this stuff, and now it's like, okay, so what do you do with this? You do a lot with this. This stuff is really useful. Um, so like I think I was just watching a video, and there was like a dude, and he had a robot, and the people were like basically it was at like a symposium or something, but they were like watching this robot like pour bottles of beer and like sweep the floor, and they were like, oh wow, this is so amazing, how's it doing all of this? Well, the trick is that the robot was remotely controlled by a human. But the thing about it is that the robot looked so convincing, and the people actually thought the robot was doing this all on its own. So that's kind of the end state that we're looking towards with deep learning, is that there is no human in all of this. The robot does do it all on its own. Um, and this can have a lot of applications, not just sweeping, not just pouring beer, but processing images. I'm not sure if y'all saw Henry's last ML Monday, um, but I mean, I don't know. They're always late. We're all always late. I'm sorry.
Yeah,
Uh,
we posted it like late at night Monday. Sometimes even
but
Tuesday. Whenever Henry does it, it's always Tuesday.
um, we basically, I mean, like, I don't think it was reinforcement learning, but you have deep learning models which can basically take images from a video game, and you can have your video game rendered in a lower frame. I mean, lower, oh my, lower frame, lower resolution. So you increase your performance, and then you, because like Nvidia has like freaking the RTX series, which can do like tensors like super well and all of this other crap. Um, Basically, you can have a model working on your computer that will take this low resolution image and scale it up to 1080p by uh, inferring what the image looks like. And this used to be horrible technology, and now it's becoming super good technology. Because computers are beginning to get really good at learning. You also have this with natural language processing. You can see like Google Translate doing all of this kind of stuff, but I don't really know too much about that one. You can see it with drug discovery. That's definitely a great one. I can tell you, I know that there are a lot of deep learning models being made on the genome and specific gene sequences to work together and better optimize what is it inhibition and then gene transcription, and I mean like just different combinations of genes to basically optimize or I'm sorry, I think I'm putting I mean basically what they're doing is they're optimizing genes so that they can have like better proteins that are made out of these sets of the genome, these genes. And basically like you can have these different kinds of things. You can do this with I think I posted one last week or so, where they were taking uh, deep learning data sets, and they were allowing them to learn off of data from protein subsets, you know, and from these protein subsets, they could optimize better proteins, and then researchers could use that to, I don't know, what have you. Let's say, somebody has like a hemoglobin deficiency, so you're trying to re-engineer like their genetics for producing hemoglobin. You could have a model basically work on producing, I mean, like using that same kind of reward function. I mean, it's not as simple in this case, but that same reward function, whenever you scale it up with more complexity, um, could produce better proteins for people who have deadly diseases, things like that. Yeah, I don't know. There's a lot of super cool stuff that you can do with deep learning. Um, Cars is another one, you know. You can see on like the highways, cars are starting. I mean, like with Tesla especially, they're using deep learning to improve driving and have self-driving cars. That is very cool stuff.
Yeah, really, whenever you think of AI, like if you ask someone on the street, like, what is AI, they'd be like, oh, robots that do things for you, kind of. But that's not quite the case. But really, deep learning is what most people think of when you think of AI. It's trying to get machines to learn like humans, and then applying that to, all that stuff Joaquin was talking about earlier. So yeah. Oh, we do not have time for this. No, we don't. Oops. No, no. Yeah, it's about 10:01. Thank you guys so much for coming. And if you have any questions, feel free to ask. I think that's it, right, Joaquin? Anything you want
No,
to add?
no problem.
Of course. Thank
Good
you
night.
for coming.
This was very long.
Yeah.
Okay. I completely dropped my like genetics example.
Okay, hold on. How do I? Okay, stop.
Oh